Hello and welcome to Data Science for Ecologists in R. In the last video, we looked at a more advanced application of the linear model. However, we did not check if the assumptions of the linear model are fulfilled. In this video, we will look at the same model as last video and begin to check the model assumptions. More specifically, we will get to know the residual plot, which is a very powerful tool for this task. With the help of the residual plot, we can check the assumption of linearity, the assumption of independent errors, and the assumption of homoscedastic errors, which is just a synonym for errors with equal variance. So let's dive right in. We start by fitting the linear model for the height of trees that we know from the last video and save it in the variable model1. To check if the model assumptions are fulfilled, we can look at diagnostic plots. We can obtain these plots by using the plot function on our model object. Furthermore, we can specify which diagnostic plot we want. The residual plot is the first diagnostic plot. On the x-axis, we have the fitted values, which are the height values predicted by our model. And on the y-axis are the residuals, which are, as we know, the deviations from these predictions. In this case, it looks like the residuals have a mean of 0 and a similar variance for all observations. Furthermore, there don't seem to be any patterns in the residuals, which suggests that there are no severe dependencies between different observations. The way this plot looks actually suggests that the three assumptions mentioned at the beginning of the video are fulfilled. Since it may not be immediately clear why this is the case, let's consider an example of a violation for each of these assumptions. An example where the assumption of homoscedasticity is violated can be easily obtained by using the same dataset. Instead of the more complex model above, we could just naively fit a simple linear model with the height as the outcome and the year as an explanatory variable. If we plot the height against the year, we see that the variance of the residuals increases over time, which suggests that the homoscedasticity assumption is violated. This way of visualizing the data is of course only possible if there is only one explanatory variable. If this is not the case, we have to rely on the residual plot, which can be used no matter how many explanatory variables there are. In this case, it just shows the same pattern of an increasing variance. For this example, we can also identify the reason for the violation of homoscedasticity. The trees differ in the average sun time per day and the experimental condition they are in. This leads to different growth rates, which naturally results in larger and larger differences in height over the years. Alright, I hope this way of checking the homoscedasticity assumption is quite intuitive. Unfortunately, it might not be enough to only look at this plot to check this assumption. For example, the homoscedasticity assumption might be fulfilled, even though the residual plot looks like it isn't. If you are interested in why this is the case, I recommend you to read about the leverage of an observation. If you just want to be on the safe side, all you have to do is look at the third diagnostic plot. Instead of the raw residuals, this plot uses the standardized residuals, which take the leverage into account. If the red line is not roughly horizontal, as can be seen in this plot right here, the homoscedasticity assumption seems to be violated. Okay, let's now come to an example where the assumption of independent errors is violated. So let's load some new data, fit a linear model, and plot the model variables. Here we can see that the residuals of values that are close to each other in time tend to be very similar, which leads to a very characteristic snake-like pattern in the residuals. This so-called autocorrelation of errors often arises in time series data, where the measurement at one time point depends on the measurement at previous time points. In the residual plot, we can see the same pattern. Finally, let's look at an example where the linearity assumption is violated. So let's load some new data for that and fit a linear model. If we plot the model variables, we can see that there is a slight curve such that the estimated linear function doesn't seem to adequately represent the true relationship between the variables. This is reflected in the fact that the residuals tend to be systematically above or below the estimated function at different time points. For example, in year 4, almost all observations are above the estimated function. As always, the same pattern is also visible in the residual plot. Alright, I think these are enough assumptions for today, so stay tuned for the next video where we will continue checking the assumptions of the linear model. See you soon!